In 1966, a man named Bruce McLaren built a race car in his backyard in England and drove it to victory on the other side of the world. The car had no business winning. The team had no budget, the engine was borrowed, and the entire motorsport establishment looked at what McLaren was doing and said, politely, that it was a waste of time. 3 years later, McLaren cars finished first, second, and third at Le Mans. Then they did it again. Then they built a road car that top engineers at Ferrari privately admitted scared them. This is legacy motoring, and I spend way too much time thinking about the engineering decisions that changed racing forever. If you're someone who loves the stories behind the machines, not just the wins, but the obsessive, irrational, beautiful thinking that produced them, make sure to hit the subscribe button and give this video a thumbs up if this helps you out. Because today, we're talking about one of the most copied, most influential, and least credited chassis philosophies in the history of motorsport. We're talking about how a small team of people, working with less money than their competitors spent on hotel rooms, accidentally solved a problem that had been holding racing cars back for over a decade. And here's the thing. The solution was so elegant, so obvious in hindsight, that when the big teams finally understood what McLaren had done, they didn't just copy it, they were embarrassed they hadn't thought of it first. But before we get into that, we need to talk about what racing cars looked like in the early 1960s, because if you don't understand the problem, you can't appreciate the solution. And the problem, honestly, was the engine. Look, when you think about a racing car from that era, a Formula One car, a sports prototype, anything built to go fast in a circle or around a road course, the engine was always at the front. That was the tradition, that was the logic. You put the heavy thing at the front, the power goes backward to the rear wheels through a drive shaft, and the driver sits in the middle somewhere trying not to die. It made intuitive sense. It was how road cars worked. It was what every engineer had grown up around. Here's what most people don't realize, though. Intuitive sense and actual physics are not always the same thing. And in the case of front-engined racing cars, they were very different things indeed. The problem with putting the engine at the front is weight distribution. Specifically, you end up with too much weight over the front axle and not enough over the rear where the power is actually being delivered to the ground. This matters enormously in a racing car because the amount of grip a tire can generate is directly related to how much weight is pressing down on it. A rear tire that isn't weighted correctly will spin, skid, and generally refuse to do its job at precisely the moment you need it most, when you're accelerating out of a corner. Now, engineers in the 1950s weren't stupid. They understood this problem. They tried to solve it in all kinds of ways. They moved fuel tanks around. They adjusted suspension geometry. They experimented with different weight distributions within the front engine layout. Some of them got quite good at managing the problem, but they were, to use an analogy, rearranging furniture in a house with the wrong floor plan. They were optimizing within a fundamentally flawed constraint. The constraint being, obviously, that the engine was at the front. Here's where it gets really interesting, because the idea of moving the engine to the rear wasn't new in the 1960s. It had been tried. Ferdinand Porsche had built rear-engine cars before the Second World War. Auto Union had raced them successfully in Grand Prix racing in the 1930s. The concept existed, the knowledge existed, and yet somehow, by the 1950s, front-engine designs had reasserted their dominance, and the conventional wisdom had quietly decided that rear-engine cars were a curiosity, not a solution. Why? Partly tradition. Partly the fact that the Auto Union cars, fast as they were, had a reputation for being nearly impossible to drive. They were terrifying machines that killed several people. Partly because the handling characteristics of that much weight at the rear were poorly understood. Engineers looked at those deaths and drew the wrong conclusion. They decided rear-engine cars were dangerous, when what they should have concluded was that rear-engine cars were dangerous when you didn't understand how to build them properly. There's a lesson in that, by the way. When a new approach fails, the question isn't whether to abandon the approach. The question is whether the failure was caused by the approach itself or by incomplete understanding of how to execute it. Most of the time, it's the latter. Most of the time, the people who give up on a new idea are the ones who couldn't figure out the execution. and they leave the door open for someone with more patience, more insight, or more stubbornness to walk through it later. Bruce McLaren was stubborn. So was his partner and chief engineer, Gordon Koppach. So in a different and more combustible way was everyone who worked in that shop in Colnbrook. They had looked at what Cooper Cars had done. Cooper had actually been the first team to win a world championship with a rear-engine Formula One car in 1959, and they had asked a question that nobody else was asking. If this works in Formula One, why are we still building sports cars with the engine in the front? Now, you might be thinking, surely the big manufacturers had already asked this question. Ferrari, Ford, Aston Martin, these were organizations with hundreds of engineers and budgets that would make your eyes water. They had asked the question, but they had also already invested enormous amounts of money in their existing designs. Sunk cost is a powerful force, even for people who should know better. Especially for people who should know better, actually, because the smarter you are, the better you get at rationalizing why your existing approach is still the right one. McLaren didn't have that problem. They had no legacy architecture to protect, no previous design to justify. They had a blank sheet of paper and a problem to solve. What they built on that blank sheet of paper would go on to win at Le Mans, influence every serious sports car manufacturer on Earth, and establish a set of principles that engineers are still working from today. The first test was at Goodwood on a Tuesday morning in late 1965, and the car was faster than anything McLaren had built before. Not marginally faster, meaningfully, undeniably, embarrassingly faster. The kind of faster that makes engineers go quiet and start doing mental arithmetic about everything they thought they knew. The second test, 3 weeks later, nearly killed the driver. Here's why that was actually progress. When you move the engine to the rear of a sports racing car, you don't just move weight, you change the entire dynamic personality of the vehicle. The front becomes lighter, more responsive, almost nervous. The rear becomes planted, grippy, reluctant to let go. In theory, this is exactly what you want. In practice, it creates a new problem that nobody had fully solved yet, a problem called oversteer snap. See, a front-heavy car, when it loses grip, tends to understeer. The nose washes wide. It's predictable, recoverable, the kind of thing a driver can feel building and respond to before it becomes a crisis. It's boring and slow, but it's manageable. A rear-heavy car, when it loses grip, does the opposite. The tail steps out. And if the weight transfer happens fast enough, if the balance tips past a certain threshold, the car doesn't just slide. It rotates, instantly, violently, with almost no warning. The driver on that second test was a man named Chris Amon, who was at that point one of the most talented young drivers in the world, and who would spend the rest of his career being in exactly the wrong car at exactly the wrong moment, which is perhaps the saddest recurring theme in motorsport history. But on that Tuesday at Goodwood, Amon did something that separated great test drivers from good ones. He didn't just report that the car had tried to kill him. He described with precision exactly what it had done, the sequence of events, the moment the rear had let go, the rate of rotation, how much warning he'd had, which was almost none. That information was worth more than 1,000 hours of theoretical analysis. Gordon Koppach took Amon's feedback back to the drawing board. And this is where the McLaren story becomes something more than just a tale about a fast racing car. Because what Koppach did next was not what most engineers would have done. He didn't stiffen the rear suspension to reduce the snap. He didn't add rear downforce to increase grip. Both of those solutions would have addressed the symptom. Koppach went after the cause. The cause, he had decided, was that the weight transfer was happening too quickly. The car was too responsive, in a sense. When the rear stepped out, the rotation happened faster than a human being could process and react. So the solution wasn't to make the rear grip harder, it was to slow down the rate at which the car transitions from grip to slip, to give the driver a warning, a moment of communication before the crisis arrived. This is a subtle distinction that most people outside of vehicle dynamics engineering would miss entirely, but it is the difference between a car that is fast and a car that is fast and drivable. And in racing, a car that is fast but undrivable is useless. It will be quick in the hands of an engineer on a test track and terrifying in the hands of a driver in traffic at 2 in the morning at Le Mans. Now, here's what most people don't realize about this period of McLaren's development. They were not operating in isolation. They were watching, very carefully, what everyone else was doing. Ferrari was still committed to front-engine layouts for their sports prototypes, though that was about to change, partly because of what McLaren was demonstrating. Ford, with its enormous American budget and its burning desire to beat Ferrari at Le Mans, had built the GT40, which was rear-engined, but was experiencing its own set of developmental nightmares. The GT40's problems were different from McLaren's, more related to aerodynamic stability at high speed than chassis balance, but the broader pattern was the same. Moving the engine to the rear created new problems that the old engineering playbook didn't have answers for. The difference between McLaren and the other teams wrestling with these issues was that McLaren had Bruce. Bruce McLaren is one of those figures in motorsport history who gets, frankly, less credit than he deserves, partly because he died young in a testing accident in 1970 before he could accumulate the kind of legendary status that requires decades of presence. But the people who worked with him describe someone with a quality that is rarer than raw intelligence and engineering. He had taste. He knew which problems mattered and which ones were distractions. He could sit in a car for 3 laps and come back with a diagnosis that his engineers would spend 2 days verifying in data, and they would find he was right. There's a version of the story where McLaren is simply a talented driver who happened to be in the right place at the right time. That version is wrong. The decisions that shaped the M6, the car that would eventually dominate at Le Mans and win the Can-Am championship with a kind of contemptuous ease that left other competitors questioning their career choices, those decisions were Bruce's. The aerodynamic philosophy, the weight distribution targets, the choice to prioritize drivability over outright peak grip, because Bruce understood something that took other teams years to learn. A car at 90% of its limit that a driver can operate confidently is faster than a car at 100% of its limit that a driver is scared of. This sounds obvious when you say it out loud. It is apparently not obvious when you are an engineer who has spent 6 months optimizing a suspension geometry and you are emotionally invested in extracting every last fraction of grip from your design. Objectivity is hard when you've done the work. Bruce had objectivity almost as a natural gift. The other thing Bruce had, and this is the detail that tends to get lost in the broader narrative, was a genuine understanding of manufacturing constraints. McLaren didn't have Ferrari's resources. They couldn't machine exotic components to thousandths of an inch tolerance and throw them away after one race weekend. Everything they built had to be robust, had to be maintainable by a small crew under pressure, had to survive the kind of abuse that endurance racing inflicts on machinery. This constraint, which looked like a disadvantage, turned out to be a gift. Because when you cannot afford to build something fragile and exotic, you are forced to find solutions that are simple and durable. And simple, durable solutions tend to be better solutions. They tend to be solutions that work when conditions change, when the temperature drops, when the track surface is different from what you tested on, when the driver is on his 19th hour of a 24-hour race and his inputs are getting sloppy. The Ferrari approach, which was to build the most technically sophisticated thing possible and then manage its complexity, broke down under those conditions. The McLaren approach held together. By early 1966, the chassis philosophy was essentially locked in. The rear engine layout, the specific weight distribution targets, the suspension tuning philosophy prioritizing progressive breakaway over maximum peak grip. The aerodynamic approach, which at this stage was relatively conservative but pointed in the right direction. On paper, the car looked good. In testing, the car felt good. What nobody knew yet was whether good would be enough. Le Mans in 1966 was shaping up to be the most competitive racing years. Ford had thrown its full industrial might at the problem. Ferrari was not going to surrender its home turf without a fight. And there, among the giants, was a small team from Conebrook with a car built in someone's backyard on a budget that wouldn't have covered Ford's catering bill. What happened next, most people in motorsport remember as Ford's story. The famous 1-2-3 finish, the corporate triumph over Ferrari, the Hollywood ending that was literally turned into a Hollywood movie decades later. But there was another story happening that week. quieter, and in some ways more important, about what McLaren learned from running their car against the best competition in the world, and how those lessons would come back with interest in the years that followed. By 1967, McLaren had the answer. The problem was nobody believed them. And honestly, you can't entirely blame the skeptics. The answer looked wrong. It violated instincts that experienced racing people had developed over decades. It contradicted what the data from other teams seemed to be showing. And it came from a small operation that, by the standards of the sports establishment, had no particular right to have figured something out that Ferrari and Ford hadn't. Here's the thing about being right when everyone thinks you're wrong. The burden of proof is entirely on you. You can't just say the thing. You have to demonstrate it, repeatedly, under conditions that eliminate every possible alternative explanation, until the people who disagree with you run out of objections. That process takes longer than it should, costs more than it should, and requires a specific kind of psychological resilience that is genuinely rare. McLaren had that resilience, but in 1967 it was being tested in ways that would have broken a less committed organization. The specific thing McLaren believed, the thing nobody else was ready to accept, was about aerodynamic downforce and where it should be applied. This requires a small detour into physics, but stay with me because this is the part that actually explains why modern racing cars look the way they do. When a car moves through air at speed, the air exerts forces on every surface. Some of those forces push upward, reducing the effective weight of the car, and therefore reducing grip. Some push downward, adding effective weight and increasing grip. The ratio and distribution of these forces determines, to a significant degree, how fast a car can corner. More downforce, more cornering speed, in principle. By 1967, most serious racing teams understood this at a basic level. They knew downforce was good. They were experimenting with spoilers, with modified body shapes, with various ways of generating more of it. The approach was essentially additive. Take the existing car shape, add bits that create downforce, see if it goes faster. McLaren looked at this approach and identified a problem with it that nobody else seemed to be talking about. The problem was drag. Downforce and drag are, in aerodynamics, deeply connected. Almost every device that generates downforce also generates drag, resistance to forward motion, and drag is the enemy of straight-line speed. So the teams adding downforce to their cars were simultaneously making their cars slower on the straights. They were trading top speed for cornering grip, and on most circuits, certainly at Le Mans with its long Mulsanne straight, this was not an obviously good trade. Now, you might be thinking, surely everyone understood this. Surely the teams were aware of the drag penalty they were paying. They were aware of it. What they hadn't done, and this is the crucial thing, was question whether the downforce they were generating was being applied in the most efficient way possible. They were accepting a certain drag to downforce ratio as if it were a fixed relationship, a law of nature, when actually it was just a consequence of the specific design approaches they were using. Koppuk and McLaren had started asking a different question. Instead of how do we generate more downforce, they were asking how do we generate downforce more efficiently? How do we get the aerodynamic grip we need while paying the smallest possible drag penalty? The answer they arrived at involved the underbody of the car. Here's what most people don't realize about aerodynamics in the 1960s. Most of the attention, most of the experimentation was focused on the top surfaces of the car. The wings, the spoilers, the body shape above the center line. The underside of the car was largely ignored, treated as a packaging necessity rather than an aerodynamic opportunity. You put the exhaust there, you put the suspension members there, you made it as clean as you could and moved on. But air flows under a car just as it flows over one. And if you shape that underside carefully, if you create a specific relationship between the car's floor and the road surface, you can generate downforce from the underside of the car with a much more favorable drag to downforce ratio than any wing or spoiler can achieve. The principle is related to what happens under an airplane wing, but inverted. Instead of generating lift, you're generating the opposite. This concept, which would eventually evolve into what engineers call ground effect, was not fully developed in 1967. McLaren wasn't running a full ground effect car. The understanding was incomplete and the technology to fully exploit it didn't yet exist. But the direction was right. The question being asked was right. And the cars McLaren built in this period reflected an emerging philosophy about using the whole car as an aerodynamic device, not just the visible bits sticking up into the airstream. The results on track were suggestive, not conclusive, not yet, but suggestive. McLaren cars were achieving similar cornering speeds to competitors with less visible aerodynamic apparatus. Their straight-line speed was better because their drag was lower. In races of sufficient length, where the car that was kind to its tires and its fuel load ultimately beat the car that was fast for 20 minutes and then struggled, McLaren was increasingly competitive. But here's where the story takes a turn that I find genuinely fascinating, because what happened next had almost nothing to do with aerodynamics or chassis dynamics or any of the technical questions we've been discussing. What happened was money, specifically the arrival of it. In 1967, McLaren secured sponsorship from Goodyear Tire and from a Gulf Oil, and these relationships did something beyond just providing budget. They provided access to better materials, to more testing time, to the kind of infrastructure that allows an engineering team to iterate quickly rather than waiting weeks between tests because they can't afford the track hire. Here's the thing about iteration in engineering. The team that can test, learn, adjust, and test again fastest is usually the team that wins, not because they're smarter than everyone else necessarily, but because they're accumulating knowledge faster. Every test session is a data point. Every data point narrows the space of possible solutions. The team with more data points finds the answer first. McLaren's new resources didn't change the direction they were heading. They accelerated the journey. Within 6 months of securing that funding, the development pace of the car visibly increased. The suspension revisions that had been theoretical became physical. The aerodynamic ideas that had been sketched on paper got built and tested. The feedback loop between driver, engineer, and machine tightened in the way it can only tighten when resources are not the limiting constraint. By late 1967, the car that would become known as the M6 was taking shape, and it was becoming clear to the small group of people who had been watching McLaren's development closely that something significant was about to happen. Bruce himself was characteristically understated about it. There's a quote from an interview he gave around this time, and I'm paraphrasing because the exact wording varied across different publications, but the substance was something like, "We think we've understood a few things that took us a while to understand, and now we want to see if we're right." That's Bruce. No proclamations, no predictions of dominance, just quiet confidence expressed as curiosity. The venue where McLaren would find out if they were right was the Can-Am Series, the Canadian-American Challenge Cup, which in the late 1960s was arguably the most technically unconstrained racing series in the world. Can-Am had almost no rules. You could run any engine you wanted, any bodywork you wanted, any aerodynamics you wanted. The cars were essentially rolling laboratories, and the competition attracted the best engineers and the best drivers in North America and increasingly from Europe as well. It was exactly the right environment for what McLaren was about to do. What they were about to do was demonstrate, in a way that left absolutely no room for argument, that everything they had been working toward for the previous 3 years actually worked. Not just in testing, not just in favorable conditions, but in race after race after race, against the best opposition available in a series specifically designed to reward pure engineering excellence. The M6 made its Can-Am debut in September 1967. Bruce McLaren and Denny Hulme, his teammate, were the drivers. The opposition included cars from Lola, from Chaparral, from Ferrari, from independent constructors who had spent their own years developing their own ideas about how to go fast. The M6 won 5 of the 6 races that season. Bruce took the championship. Hulme finished second. It wasn't close. It wasn't a matter of the other teams having bad luck or making mistakes. McLaren was simply, measurably, consistently faster. The car worked. The philosophy worked. Everything that Koppuk had been working out on paper and Bruce had been feeling in the seat and refining through 3 years of incremental development had converged into something that was, for that moment in time, the best racing car in the world. And the skeptics, the ones who had looked at the rear engine layout and the understated aerodynamics and the unfashionable emphasis on drivability over peak grip, finally went quiet. Not because they had been convinced intellectually, because the results had made argument impossible. That's usually how it goes. The moment McLaren won everything, the rest of the sport started copying them. What they copied wasn't the car, it was the thinking. And most of them got it wrong. This is actually one of the most instructive patterns in the history of motorsport engineering, and it repeats itself with remarkable consistency across different eras and different series. A team develops something genuinely new, demonstrates that it works, and then watches as competitors attempt to replicate it. The replication almost always fails initially, not because the idea was wrong, but because the copycats are reproducing the output without understanding the process that produced it. Think about what that means in practical terms. When you look at the M6 and decide to build something similar, what you see is a rear-engined layout, certain aerodynamic proportions, a particular suspension geometry. What you cannot see is 3 years of iterative testing. You cannot see the specific failure mode that led Koppuk to change the rear suspension pickup points in the spring of 1966. You cannot see the conversation between Bruce and the tire engineers that shifted their thinking about load distribution. You cannot see the 100 small decisions that seem arbitrary in isolation, but form a coherent philosophy when understood together. So you build the thing you can see, and it doesn't work as well as the original. And you conclude, wrongly, that you must be missing some secret ingredient, some piece of hardware or some measurement that McLaren is keeping to themselves, when actually what you're missing is the understanding. The hardware is almost secondary. Here's what most people don't realize about competitive advantage in engineering. It is almost never a single breakthrough. It is almost always an accumulation of correct small decisions, each one individually modest, collectively decisive. The team that beats you hasn't discovered a magic component. They've made slightly better choices, consistently, across dozens of decisions you weren't even aware were decisions. This is both encouraging and maddening, depending on your perspective. Encouraging because it means there's no single secret to find, no locked door behind which the answer is hiding. Maddening because it means the gap can only be closed through the same patient, iterative, fundamentally unglamorous process that created it in the first place. There are no shortcuts. The teams chasing McLaren in 1968 were looking for shortcuts. Chaparral, the American team funded by Jim Hall, took perhaps the most dramatic approach. Hall was a genuine engineering visionary, a man who had independently arrived at several of the same aerodynamic insights as McLaren, and in some areas had gone further. His 2H car for 1968 featured an enormous rear wing mounted on struts high above the bodywork, generating massive downforce at the cost of equally massive drag. It was spectacular to look at. It was terrifyingly fast through corners. And it was, on balance, not faster than the McLaren over a full race distance, because the drag penalty on the straights was too severe. Hall understood the downforce principle. He hadn't yet understood the efficiency principle, the idea that how you generate downforce matters as much as how much you generate. Lola, the British constructor, took a more conservative approach and got closer to McLaren's pace, but couldn't quite match it. Their car was well-built and well-driven, but lacked the specific aerodynamic insight that made the M6 work at the level it did. They were, in the language of the time, a good car in a series that had a great one. And then there were the privateers, the independent teams running older McLarens, older Lolas, cars that had been fast a year or two earlier and were now being outpaced by the factory teams. These teams are actually important to the story because of what happened to them over the following seasons, which is that McLaren started selling them current specification cars. This was a commercial decision that turned out to be an engineering revelation. When McLaren began selling the M8 series cars to customer teams, something interesting happened. The customers, who were paying significant money for these machines and had strong motivation to understand them fully, started providing feedback that the factory team hadn't anticipated. They were running the cars in different conditions, on different tracks, with different drivers of different skill levels, and they were discovering things about the car's behavior that only revealed themselves outside the narrow corridor of conditions that factory testing had explored. Some of this feedback was immediately useful. Some of it pointed toward problems that the factory team had been unknowingly compensating for through driver skill and setup adjustments without realizing it. The customer program, in other words, became an involuntary but highly productive extended testing program that deepened McLaren's understanding of their own car. Bruce was smart enough to pay attention to this feedback rather than dismiss it. A lesser organization might have seen customer complaints as noise, as evidence that the customers were running the car incorrectly rather than evidence that the car had characteristics worth examining. McLaren treated every piece of customer feedback as potentially valuable data. Some of it wasn't, some of it was gold. The 1968 Can-Am season was, if anything, more dominant than 1967. McLaren won again. Holm took the championship this time, with Bruce second. The orange cars, as they had become known, were so consistently fast that the series was beginning to acquire an unfortunate nickname among competitors, the Bruce and Denny Show. It wasn't meant entirely as a compliment. But here's where I want to draw your attention to something that gets almost no coverage in the standard telling of this story. While McLaren was winning races and championships and accumulating the kind of competitive dominance that motorsport history remembers, the more important work was happening away from the track entirely. Kopic and his team were not resting on the success of the M6 and M8. They were, with the methodical obsessiveness that characterized everything McLaren did in this period, working on the next problem. And the next problem was one that their success had actually made visible. When you are winning comfortably, you have a luxury that teams in the middle of the field don't have. You can afford to look at your car not just in terms of what it does well, but in terms of what it could theoretically do better. You can run experiments that might not pay off immediately because you have enough margin in hand that a few lost development cycles won't cost you a championship. Winning creates the conditions for the kind of long-horizon thinking that produces the next generation of innovation. What the McLaren engineers were seeing when they looked at their winning car with honest eyes was that the aerodynamic efficiency they had been pursuing was hitting a ceiling. The underbody work they had been doing was producing results, but those results were increasingly marginal. The gains were getting smaller with each iteration. They were approaching the limit of what was achievable within the current aerodynamic philosophy. To go further, they needed a new philosophy. The concept they were circling around, without yet fully grasping it, was what would eventually become ground effect in its mature form. The idea that you could use the space between the car's floor and the road surface as an aerodynamic tunnel, creating a low-pressure zone that literally sucked the car toward the ground. Not just reducing lift, actively generating downforce through suction, through a pressure differential between the underside of the car and the atmosphere above it. The physics of this were understood in principle. The engineering challenge was immense. You needed to seal the sides of the car to maintain the pressure differential. You needed a floor shape that created the right airflow characteristics. You needed suspension that could maintain a consistent ride height, because the ground effect was highly sensitive to the gap between floor and road. Change that gap by a small amount, and the downforce could change dramatically, making the car either terrifyingly grippy or terrifyingly not, depending on which direction the gap moved. In 1968 and 1969, McLaren was probing at the edges of this understanding. They weren't ready to commit to a full ground effect design. The technical risks were too high, the understanding too incomplete. But the work they were doing in this period was laying the foundation for what would eventually become one of the most dramatic performance leaps in racing history. Meanwhile, something else was happening that would change the context for all of this development work. The broader world of motorsport was beginning to catch up to where McLaren had been 3 years earlier. Teams that had been skeptical of the rear-engine philosophy were now fully committed to it. Teams that had dismissed aerodynamic efficiency as secondary to raw downforce were beginning to understand their mistake. The gap between McLaren and the field, while still significant, was narrowing. Not because McLaren had stopped developing, because the field had started developing in the right direction. And when the gap narrows in motorsport, the pressure to find the next leap intensifies. Second place is the first loser, as the saying goes. McLaren had been first for 3 years. The question now was whether they had enough in reserve to stay there. Bruce McLaren, as the 1970 season approached, was confident they did. He had seen the work Coppock was doing. He understood where the development was heading. He had that quality of certainty that comes not from arrogance, but from genuine comprehension of a subject. The certainty of someone who has done the work and knows what the work is pointing toward. He would not live to see it arrive. On June 2, 1970, Bruce McLaren died testing a car at Goodwood. What happened to the team in the weeks that followed is one of the most remarkable stories in motorsport. The car was the MAD, the latest evolution of the Can-Am machine. Bruce was alone on the circuit, doing what he had done hundreds of times before, working through a methodical test program, feeling for the things that instruments couldn't measure. A rear bodywork section failed at speed. The car left the track at a corner called Levant. Bruce died at the scene. He was 32 years old. The phone calls that followed are difficult to imagine. Teddy Mayer, who ran the business side of McLaren, took most of them. Denny Hulme, Bruce's teammate and close friend, heard the news in New Zealand. The workshop in Colnbrook, which had been buzzing with preparation for the upcoming Can-Am season, went quiet in a way that workshops almost never go quiet. And then, after a period of grief that nobody outside that team can fully measure, something happened that says everything about the culture Bruce McLaren had built. They went back to work. Not immediately, not callously, but deliberately and with a clarity of purpose that Bruce himself would have recognized and approved of. The Can-Am season was approaching. There were cars to prepare, a championship to defend, a team of people whose livelihoods and identities were bound up in the continuation of what Bruce had started. Stopping would have been understandable. It would also, everyone in that workshop understood, have been wrong. Here's the thing about organizations built around a singular visionary. The conventional wisdom says they collapse when the visionary leads. The founder departs, the energy dissipates, the institutional knowledge walks out the door, and what remains is a shell of the original thing, sustained by momentum and reputation until reality catches up. McLaren defied this pattern. Not easily, not without cost, but definitively. The reason they defied it comes back to something we touched on earlier. The culture of understanding that Bruce had insisted upon. He had not built a team that executed his ideas. He had built a team that understood his thinking. There is a profound difference between those two things. A team that executes ideas is helpless without the person generating them. A team that understands thinking can continue to generate ideas in the same spirit, applying the same values and the same approach to new problems. Coppock understood the aerodynamic philosophy. Mayer understood the commercial and organizational principles. The senior mechanics understood why the car was built the way it was, not just how to assemble it. The institutional knowledge was distributed across the organization rather than concentrated in one person. Bruce had made himself, in engineering terms, somewhat redundant, which sounds like a strange thing to say about the founder of a company, but is actually one of the highest compliments you can pay to a leader. The 1970 Can-Am season proceeded. Denny Hulme drove. Peter Gethin came in as a second driver. The orange cars showed up at the first race and went fast. Hulme won. Then he won again. The team that had just lost its founder, its spiritual center, its chief development driver, won the 1970 Can-Am Championship. Think about that for a moment. Genuinely sit with it. The man who built the team died 2 months before the season started. The team won anyway. Not through luck, not through the residual momentum of a dominant car, through the quality of the people Bruce had hired and trained and trusted with the understanding of what they were trying to do. Now, I want to be honest about something here because this story has a complication that the triumphant version tends to skip over. The 1970 championship, dominant as it was won with a car that Bruce had largely developed before his death. The MAD was his car in every meaningful sense. Winning with it was a tribute to him, but it wasn't a test of whether the team could innovate without him. That test came later, and it was harder. The 1971 season brought new competition. Porsche had entered the Can-Am series with serious intent and serious resources, deploying the turbocharged 917, a car that generated power figures that made the McLaren's big block Chevrolet engine look almost modest. Jackie Stewart, who knew something about going fast, described the 917 in full Can-Am specification as the most powerful racing car he had ever driven. He did not mean this as a compliment to the experience of driving it. McLaren faced, for the first time in several years, a genuine performance deficit. The Porsche had more power. On the long straights that featured on many Can-Am circuits, there was simply no answer to it. You can tune your aerodynamics and refine your chassis all you like, but if the other car has 300 more horsepower, the straights are going to hurt. This is where the post-Bruce McLaren team faced its first real creative test. The car they had inherited was optimized for a competitive environment that no longer existed. The assumptions underlying its development, particularly around the engine power available, had been invalidated by Porsche's arrival. Something new was needed. What Koppuk and the team came up with was not a single dramatic innovation, but a systematic re-examination of where time was being lost and where it could be recovered. The aerodynamic efficiency work intensified because efficiency was now more valuable than ever. If you couldn't match the Porsche on the straights, you had to beat it everywhere else, through corners, through braking zones, through the countless transitions that make up a lap of a real racing circuit. The underbody work that Bruce had been pointing toward accelerated. The team was now pushing harder into ground effect territory, not yet with a fully developed system, but with increasing commitment to the principle. The ride height sensitivity problem was being studied more seriously. The ceiling question, how to maintain the pressure differential under the car across varying track surfaces and suspension movements, was moving from theoretical discussion to active development. This is where I want to introduce a concept that I think explains a lot about why McLaren survived and thrived through this difficult period. The concept is what I'd call principled adaptation. There's a version of loyalty to a founder's vision that is actually a form of paralysis. Teams and organizations sometimes become so committed to the specific solutions a founder developed that they cannot adapt when circumstances change. They preserve the answers when they should be preserving the questions. The answers were right for a particular moment. The questions are right for all moments. McLaren preserved the questions. The question was never, how do we build a car that looks like Bruce's car? The question was always, how do we build the fastest, most efficient, most drivable racing car possible within the rules we're operating under? Bruce's specific answers, the rear engine layout, the aerodynamic efficiency philosophy, the emphasis on drivability, those were right answers for the problems of 1967. In 1971, with a turbocharged Porsche producing numbers that rewrote the competitive landscape, some of those answers needed updating. The team updated them, without sentimentality, without drama, with the same methodical rigor that Bruce had instilled in everything they did. The Porsche era of Can-Am, as it's sometimes called, was genuinely difficult for McLaren. They did not dominate the 1971 and 1972 seasons the way they had dominated earlier years. They won races, but not championships. For a team accustomed to the kind of systematic superiority that had earned them the Bruce and Denny Show nickname, this was uncomfortable. But here's what most people miss about this period. The adversity was productive. The pressure Porsche applied forced McLaren to go places aerodynamically that they might not have gone otherwise. The ground effect development that had been proceeding at a measured pace accelerated under competitive necessity. The understanding that was accumulating during these years, hard-won through the experience of racing a car that wasn't quite fast enough and having to figure out why, would prove decisive when applied to a new generation of machinery. And there was something else happening during this period that the race results don't capture. McLaren was building a Formula One operation. The Can-Am program had always been partly a commercial and partly a developmental exercise. The lessons learned there, the manufacturing processes, the aerodynamic insights, the organizational culture, were being transferred to a Formula One effort that was growing in ambition and capability. In 1974, Emerson Fittipaldi drove a McLaren Formula One car to the World Championship. It was the M23, a car that embodied everything the team had learned through a decade of Can-Am development and applied it to the most technically demanding racing series in the world. The weight distribution philosophy, the aerodynamic efficiency approach, the commitment to drivability, all of it translated into Formula One. The M23 was not a revolutionary car in the way that, say, the Lotus 78 would be revolutionary a few years later with its fully developed ground effect system. It was something perhaps more valuable. It was a car that worked reliably, consistently, across different tracks and different conditions and different drivers. It expressed the accumulated understanding of an organization that had been asking the right questions for a decade. James Hunt won the championship in 1976 in the same basic car, updated but philosophically consistent. 2 championships in 3 years with a machine that traces lineage directly back to the ideas Bruce McLaren had been developing in that workshop in Colnbrook in 1965. The founder was gone, the thinking remained, and the thinking kept winning. The last thing McLaren built in the 20th century wasn't a racing car, it was a road car, and it was so far ahead of everything else that it took the industry 15 years to catch up. The McLaren F1 was conceived in 1988 by Gordon Murray, who had joined the organization after years of designing championship-winning Formula One cars at Brabham. Murray is one of those engineers who thinks in a register slightly above where most people operate, not just technically but philosophically. He doesn't ask, how do we build a fast car? He asks, what does a fast car actually mean, stripped of assumption and convention, and then he builds that thing instead. What Murray decided a fast road car meant was this. It meant the lowest possible weight. It meant the highest possible power-to-weight ratio. It meant aerodynamic efficiency rather than aerodynamic spectacle. It meant a driving experience so pure and so communicative that the person behind the wheel felt not like a passenger being transported quickly, but like an extension of the machine itself. And it meant a 3-seat layout with the driver in the center, flanked by 2 passengers slightly behind, because that was the geometrically correct place for the driver to sit if you were being honest about sight lines, weight distribution, and the fundamental geometry of a high-performance vehicle. That last detail tells you everything about Murray's approach and about the McLaren culture that had shaped it. Nobody asked for a center seat layout. No focus group requested it. No competitor had done it. Murray arrived at it through first principles reasoning, decided it was correct, and built it that way. The fact that it was unconventional was irrelevant. The fact that it was right was everything. The F1's development ran from 1988 to 1992, when the first customer cars were delivered. The budget was essentially unlimited, which sounds like an advantage and mostly was, except that unlimited budgets create their own problems. When cost is not a constraint, you are forced to make decisions purely on merit. And making decisions purely on merit is actually harder than it sounds when every option is theoretically available to you. Murray responded to this challenge by imposing his own constraints, not financial ones, but philosophical ones. Every decision had to be justified by its contribution to the core objectives: weight, power, efficiency, feel. If a component didn't serve those objectives, it didn't go in the car, regardless of how impressive it might look or how much it cost. The engine is probably the most famous example of this philosophy. Murray wanted a naturally aspirated engine of specific dimensions and weight. He approached several manufacturers. Most of them either couldn't meet his specifications or weren't interested in the project. BMW Motorsport eventually built what Murray asked for, a 64-valve V12 displacing 6.1 liters and producing, in road car specification, 627 horsepower. It weighed 266 kilograms. It was, by any measure, one of the greatest internal combustion engines ever built for a road vehicle. But here's what most people focus on with the F1, and what most people consequently miss. The engine, spectacular as it was not the point. The engine was a solution to a requirement. The requirement was a specific power-to-weight ratio, achieved through a specific combination of power output and vehicle mass. Murray would have used a different engine if a different engine had met the requirement better. The F1's genius was not the BMW V12. The BMW V12 was a consequence of the F1's genius. The car weighed just over 1,000 kilograms fully fueled. In an era when comparable performance cars from Ferrari and Lamborghini weighed significantly more, this was extraordinary. The carbon fiber construction, which McLaren had pioneered in Formula One and was now applying to a road car for the first time in serious production, was responsible for much of this. The attention to weight at every level of the design was responsible for the rest. Murray famously cleaned components with a hairdryer rather than compressed air during assembly, because the compressed air left the residue that added measurable weight. That is either obsessive or visionary, depending on your perspective. Probably both. The F1 went on sale in 1992 for just under £500,000, which even then was an almost incomprehensible sum for a road car. McLaren built 106 of them. In 1998, a standard F1 set a production car speed record of 240 miles per hour that stood for years. In between, the racing version of the car, entered at Le Mans almost as an afterthought, finished first, third, fourth, fifth, and 13th in 1995 against purpose-built racing cars from manufacturers who had spent years preparing specifically for that race. That Le Mans result is worth pausing on. A road car, modified for racing but fundamentally a road car, went to Le Mans and won. Not because McLaren had built a secret racing machine disguised as a road car, but because the principles underlying the F1's design, low weight, aerodynamic efficiency, mechanical integrity, were the same principles that win endurance races. The road car and the racing car, in McLaren's philosophy, were expressions of the same thinking. Of course the road car could win at Le Mans. The question, if you understood what Murray had built, was why anyone was surprised. The F1 connected something that had begun in a workshop in Colnbrook in 1965, a set of questions about what a fast car actually was and how to build one honestly, to a conclusion that the broader automotive world spent the following decade and a half trying to absorb. Every lightweight, aerodynamically efficient, driver-focused performance car built since owes something to what Murray articulated in the F1. Not because manufacturers copied specific components or specific dimensions, but because the F1 demonstrated with the same unanswerable clarity that the M6 had demonstrated at Can-Am that the approach was correct. One team, 30 years. A backyard workshop to the fastest road car in the world. The thinking never changed, only the machines it expressed itself through. That is the McLaren story. And it started with a man who refused to accept that the engine had to be at the front.